Hi, thank you very much for watching this video. Today I will talk about my doctoral work on the topic of embodied interaction in virtual reality for grounding mathematics. And before we start, there's actually a little exercise for you. So if you could stop for a minute and try to remember and think about how you felt during your last math lesson. At this point, maybe you feel like many students. Maybe you feel that math is something that you had to do alone, that it was only for extraordinary students, and that it had nothing to do with the real world. And that's how many students feel. However, if you ask mathematicians and practitioners how they feel about their field, they're going to give you much more exciting and intriguing definitions. They will tell you that math is the largest coherent artifact that's been built by civilization, that it's the longest continuous human thought, or that it's an ideal reality. What's important here is that mathematicians roughly agree that math is something that we do together, that has space for change and modifications, and also space for diversity. And when I started looking into those topics, I got quite curious about whether or not we can reconnect abstract mathematics to the real world. And here the idea is that this would maybe be a more accurate way of teaching mathematics and also more beneficial for students. And I started looking into that. I found the theory that math actually directly comes from the real world, that math is the result of our sensory, motor, embodied experiences with the world. And here you might ask, what does embodied mean? And I was wondering about that myself as well. And here what's important to know is that during my doctorate, I was in an interdisciplinary context between computer science and learning sciences. And as I was trying to define the term, I figured out that there are actually different meanings, slightly different meanings based on the field. So to start this presentation, I will talk about three meanings: embodied cognition, embodied interaction, and avatar embodiment. So let's start with embodied cognition. So proponents of embodied cognition are, like, often rejects the Cartesian divide between the mind and the body. And so what they say is that there's a much more intertwined relationship between the two. And specifically that if we design learning activities without considering the bodies of the learners, this could be, first of all, a fallacy, but also detrimental for learning. To give you a concrete example here, you have The Hidden Village, which is a video game that was implemented by researchers in embodied learning of mathematics. And in this game, they explicitly teach gestures for students to help them represent mathematical concepts. And what they found in these kinds of work is that gestures and bodily actions can actually help students learn, but that they have to be meaningful. So moving is not enough. The movement needs to be congruent with what you are trying to teach or to learn. To represent this within one system, we have a learner performing bodily actions. Those bodily actions represent a concept, and through this we have learning that may happen. As a short summary, the bodies of the learners help them learn. The second topic I want to talk about is embodied interaction. And here is this idea that interaction is informed by and grounded in its physical and social context. So if I want to design an interaction with a digital component, I need to consider the physical and the social world around it. Again, to give you a concrete example, this is a gesture that's a priori meaningless. When you look at it, you're not too sure what it means. However, if you consider the context in which this gesture is used, for example, the smooth surface of a mobile display, you can give meaning to this interaction. So for example here, if I'm doing this, I'm expanding the space and compressing the space. What I particularly like about this interaction is that it's not a natural interaction in the sense that we don't go around the world and zoom in and out on things by moving our fingers. However, because it has such a strong physical and embodied meaning tied to it, once you learn this interaction, you will not forget it. If we can represent this in a system again, we have a user interacting with an object. This interaction is embodied, which means it depends on a social and a physical context, and through this we may have meaning making. And here I want to insist on something quite important. When we speak of meaning making in the context of embodied interaction, we speak of making sense of the interaction itself. So let's say you have a game about derivatives with a meaningful zooming interaction like this. The fact that the interaction is embodied doesn't necessarily help students learn mathematics. Of course, the interaction is meaningful, but it has nothing to do with derivatives and it doesn't equal learning. So here I want to insist that making sense of the interaction does not necessarily support learning, and we will come back to this later. Now the last meaning I want to talk about is avatar embodiment. And in my work I was interested in virtual reality. And what happens in virtual reality is that you have two bodies to consider: the physical body of the learner, but also the avatar representation of the learner in the world. And from this comes the sense of avatar embodiment, which is about this relationship between the learner body and the digital body. And the sense of embodiment is based on three constructs. The first one is the sense of self-location, so how much is the avatar space my space? Then the sense of agency, am I in control of this digital avatar? And finally, the sense of body ownership, is this hand my hand? Again, if we represent this within one system, we have a user performing bodily actions. Those bodily actions inform an avatar that in turn interact with the digital object. So we have this puppeteering thing going on. And now we spoke about the three meanings. First, the bodies of the learners play a role in learning. Second, our bodies help us make sense of interaction. And third, there are two bodies to consider: the physical body and the digital body. And the first thing I did in my doctoral work is actually gather all of those together and build an interdisciplinary framework for the design of embodied learning activities, which is this one. And in the rest of the work, what I did is that I used this framework and I explored the different pieces of it, and to help address one main research question, which is about how to design embodied interaction to support embodied sense-making of mathematics. And in the rest of the presentation, we will deep dive into the different areas of this framework. So first, we will look into how to design the interaction. If we go back to the bigger picture, I'm trying to go from interaction to learning, and my research question is, how does embodied interaction design impact learning? To do that, I focused on the topic of derivative, and this is one of the first prototypes that we put together. And the idea was for students to get an embodied understanding of the relationship between a function and its derivative. We validated the first prototype with a qualitative study with experts, and we improved it a bit. Now we have a much more welcoming place, we have a plant, and we also have much more direct interaction. Here you can see on the video how I'm directly manipulating the curves. And I use this new prototype to answer a new research question, which is, how do different embodied interactions compare in terms of usability, but also learning outcomes? Okay, so first thing we need to do is design those different embodied interactions. To do that, I actually use two existing frameworks. So the first one looks at different degrees of embodiment, and this is based on immersion and sensory motor stimulation. And here I had two conditions, one that was with a low degree of embodiment on a tablet, so low sensory motor stimulation and low immersion, and then one where we maximize all that in virtual reality. But then what I did is that I also looked at different types of embodiment. So this condition here is position focused, which means that the position of my body represents the derivative. So here you can see me manipulating a handle that I can rotate, and at any point in time, the position of my body represents the derivative, so 0, 1, etc. And then the other type of embodiment I looked into is movement focused. And here it's my body movement that represents the derivative. How it's implemented here is that you have a point on the curve and you can drag it to draw the derivative. So my movement is the derivative. We evaluated all of this through a user study with 38 participants. We actually went into the classrooms with the high school students, and you can see a bit the setup that we installed there. And we had two interventions for the user study. In a preparatory intervention, we went there with the first pre-test and intro questionnaires, but also we played a VR game called Elixir, which is heavily focused on hand interaction. And I wanted to do that so that the students have a positive experience with virtual reality and get all their excitement out, because of course if you go to the classrooms with a VR headset, they just get very excited and it's hard to get proper results. And also I noticed in previous studies that people are not too sure what they can do in virtual reality. So here we made them a bit more comfortable with using their hands in virtual reality. We went back to the classrooms a few days to a week later, where we had like the main study about the mathematical topic specifically. And what did we learn through this study? First, when we compared different degrees of embodiment, we found that they're roughly comparable. The one in virtual reality takes longer, but that makes sense because you have to move more, so that takes more time. When we compare the different types of embodiment, we actually found something quite interesting. We found that the position-focused condition performed roughly better. It was faster, it led to less superfluous manipulations, more movement amplitude, and there's a hint that it also leads to more persistence and better learning outcomes. And I was quite curious about where the difference comes from because I didn't find necessarily differences in usability, so there has to be something else that explains those differences. And here we need to go back to the framework. In this framework, there are two paths to learning. The first one is through the bodily actions. And here, if we look at the bodily actions, we notice that they highlight slightly different mathematical meanings. So on the position-focused one with this handle, I'm actually highlighting derivatives as slopes. Like, where the slope is higher, the derivative is higher. When the slope is lower, the derivative is lower. However, on the other one, which is movement-focused, I'm highlighting derivatives as variation rates because I notice, okay, when I go higher, the derivative is higher, but I don't need to go that far. No matter how close I go, I still have the same derivative. And this is exactly how you help students learn about variation rates. However, when I looked at the interaction, which happens within a specific context, the interaction and the context of that interaction was designed to highlight derivatives as slopes. There is no idea of movement along the x-axis, no idea of movement along time, and we're focusing on specific points of the curve. So what's happening is that interaction highlights derivatives as slopes. In one case, the position-focused case, the bodily actions also highlights derivatives as slopes. So we have something congruent between interaction meaning and bodily actions meaning, and this is a condition that performs better. And for the other one, those two paths are not congruent and the condition performs a bit worse. So here, I think this means that there is a space between interaction meaning and mathematical meaning that's very interesting to explore in terms of design. How much should they be congruent for people to actually learn? Is a disruption between these congruence actually interesting for people to get opportunities to explore and question the topic? So basically, I think this is a very interesting direction for design in the future. And with this, we uncovered the interaction part of the framework. For the next project, I want to speak about learners. And what I'm interested here is about what bodily actions do learners perform when making sense of derivatives. And to do that, we need to actually improve our framework a bit. So there are two ways in which bodily actions can help people learn. First, when I am making sense of something, or when a learner is making sense of something, we spontaneously perform bodily actions. That means we need to design learning activities that support those spontaneous bodily actions. That's the first part. But then there is another context in which bodily actions happen. For example, in the derivative game I showed before, students are moving, but they're not moving spontaneously. They are moving because they are directed to do so by the activity. And this is called directed bodily actions. And in this project, I looked at both sides of the framework. To look at spontaneous bodily actions, we had a qualitative study with different students and experts on the topic of derivative, and we just looked at the gestures that they spontaneously produce. Then looking at the other side of the framework, I had a quantitative study with 130 participants this time, using the two position-focused conditions from the game before. And I don't have time to go into all the details, so I really want to focus on my favorite results. Looking at the directed bodily actions, one thing we found is that math-anxious individuals actually benefit from embodiment in virtual reality. So what happened is that on the tablet, we had relationships that we often have. So high math-anxious people struggled more to solve the problems and they got worse grades at the post-test. However, in VR, it was not the case. So you can see here how the blue line is completely flat. So one can argue that embodiment itself helps math-anxious people. What I believe is that it actually has to do with the immersive properties of virtual reality, because when you're in VR, you don't see your teachers anymore, you don't see your peers anymore, and you're not scared of judgment that much. The social cues are not triggering your math anxiety that much. So I think that's interesting to consider when designing those activities. We also find that highly body-aware individuals also benefit from embodiment in virtual reality. Now, looking at the other side of the framework, one thing I found very interesting is that mathematical meaning is expressed beyond position and movement. And this is extremely important because that's how we've been designing those interactions so far. Like in the frameworks that I mentioned before, we focus on position and movement. And here what I noticed in the context of derivatives is that the students actually used muscle tension to express derivative. So for example, if they want to show like a slope going up, I was expecting them to kind of draw the slope in one way or another, like all those different techniques. What they actually did, some of them, is they just moved the hand up or down to show whether it's going up or down. And then to express how steep it is, they use the muscle tension. So this is like a mountain going up, and this is more like a hill. And that's very interesting, again, because it expands our design space. And what we can conclude for that project in terms of future work is that it's very important to consider VR embodied learning activities because it can support math-anxious individuals, it can support highly body-aware individuals, but we can also capture position and movement out of the box and muscle tensions with sensors such as this one. And with that, we uncover the top part of the framework. The next project I want to talk about is designing the context of that interaction. Again, if we go to the framework again, I'm trying to go from physical context to learning. And the question is, how can we design the context of the interaction to support embodied sense-making of mathematics? And with that, maybe it's time to finally define grounding. So grounding is about forming a mapping between an idea or a symbol and a more concrete reference, such as an object, a movement, or an event in the world. So for example, here you have a symbolic representation and a formal representation of a flow network, which is some form of a graph. But this can be imagined and experienced and considered in terms of more concrete experiences, such as electrical networks, social networks, transportation networks, the internet, etc. And when I was thinking about this, I thought, well, actually, maybe embodiment brings a form of concreteness that can be used to anchor this grounding. And so here I was interested in something that I called embodied concreteness, which is a form of concreteness that involves a high degree of embodiment, as defined before, in a situated and relatable context. And I wanted to see if designing according to this principle actually helps students. And I tried to find some work on embodied experiences of graphs, and I didn't find much. However, I find quite some work on embodied teaching of electrical networks. And here there are two main metaphors that are used, the moving crowd metaphor and the water flow metaphor. And I found out that the water flow metaphor is the one that's most commonly used, so I thought it would also be most relatable, and that's the one we used. Here is how the game looks like. So the goal for the students is simple. They just need to bring the maximum amount of water from the lake to the city. And to do that, they can interact with the graph using their bodies. And here you can see how at any point in time, the distance between the two hands is proportional to the desired flow in the edge. And you can see here the student going around the graph and solving the problem. And we evaluated, we had a first usability study that showed that the system is very usable, and then we continued with the main study. And here I compared three different conditions. The first condition was on paper. It was the most abstract condition. It's very similar to what you do in math class. You have the problem on paper and you solve it. Then I wanted to isolate the role of feedback. So I had the same condition, but on a tablet, which I called manipulated concreteness. And here you can manipulate the graph. So you can already start like connecting with it, and you get feedback on whether what you're doing is correct or not. And then we had the full-blown embodied concreteness condition in virtual reality with this high embodied context, but also relatable metaphors. So those three conditions. We tested those with 89 bachelor students from the math department here at ETH, and we had protocol over several weeks. What did we learn from this study? Very interestingly, we found that both forms of concreteness, so the manipulated one on tablet and the embodied one in virtual reality, they both significantly increased attention and confidence. And this is quite important because confidence is the questionnaire for confidence asks questions such as, oh, I feel this is something I can do. And this challenges this assumption that math is only for extraordinary students. So just by adding this form of concreteness, we can already challenge this. What I also found interesting is that the embodied concreteness condition was the only one to significantly increase relevance. And here again is interesting because relevance is a metric that asks questions such as, oh, I understand why I have to learn this, I understand why this is a useful topic, and I understand how it's related to the real world. And here, with embodied concreteness, we can do that. So we can challenge this assumption that math has nothing to do with the real world. I had a second metric for this. After playing the game, the students went to the lecture and they had a normal lecture with their normal lecturer. And after that, I asked them whether they felt well prepared for the lecture, because I was afraid that because the most concrete representation is so far away from what they do in class that they might feel a bit the disconnection. And actually here again, the embodied concreteness condition scored significantly better. So this tells us that if we design the context of the interaction according to embodied concreteness, the students can understand why they're learning this content, they can understand what it has to do with the real world, but they can also connect it to the subsequent lecture. Okay, but that's not enough, we also need to look into learning outcomes. When I looked into learning outcomes, I found that on 2 of the post-tests, there was no difference, as shown per the Bayesian analysis here. However, on the most abstract condition, we found that the manipulated concreteness performed significantly worse. And I tried to understand this, and in the paper you can read the whole discussion about the underlying mechanisms. Here I will just briefly explain. First, when it comes to the learning differences, I think this comes from differences in feedback. Specifically, on the tablet, the students can see when they make a mistake, and this can help them build their strategy. But in the embodied concreteness condition, because they see the whole water flow going through the pipes, they can also understand why they made the mistakes. And I think this explains these differences in learning outcomes. When it comes to the difference in grounding, here I really think this is only from embodiment, and it comes from this modal priming mechanism, which is about reconnected abstract concepts to previously experienced sensory motor experiences. So here, I think the main contribution of this work is that embodied concreteness is a powerful way of grounding abstract mathematics, and it's something we should consider in the design of embodied learning activities. And here, with that, we uncovered the bottom part of the framework. And now it's time to speak about the central piece of the framework, which is the digital avatar. So how can we actually design the avatar to support all of this? Going back to the framework, I'm interested into 2 things. First, I'm interested in how the digital avatar can support meaning making of the interaction. And then I'm interested into how the digital avatar can support learning. And here again, we need to go back to theory a bit. So I mentioned that there are different meanings of embodiment. And one problem is that in the literature, those meanings are often confused one with another. So one would assume that having embodied interaction necessarily helps embodied learning. Or one would assume that high avatar embodiment necessarily supports embodied interaction and embodied learning. And in this project, we're interested in, can we actually break this? For example, what if we break morphological similarity between my body and the avatar? Is there actually a space here to explore in terms of design to help you make sense of interaction and help you learn? And so we did that through a mechanism that we call digital glove, which is about co-locating input and display on the hand of the users. And we believe this has 2 main benefits. One, it reduces the split attention effect. And second, it can give meaning to the interaction. So here, this is an example of a game, which is a pinball game that you play on your hand. And what's interesting here is that because the play field is on my hand, I have novel, meaningful, embodied interaction. For example, just connecting 2 fingers mean creating a pathway between 2 areas of the play field, very simply. And we tested this through different studies, and I found this was quite interesting. And what I also noticed is that as I interviewed the participants after the study, when they were talking about those games, sometimes they forgot the vocabulary of the game or they forgot the words. However, their hands were moving like they did in the game. So they were doing this, they were doing that to describe the games. And then I thought, okay, maybe we can use this to our advantage for learning. And I was wondering, can we actually design avatars to elicit specific bodily actions that can support people's learning? And here this is conceptual work, but I still think it's interesting to explore. What I would like to do is something called semantic avatars. Those would be digital avatars designed to highlight a specific meaning explored through bodily actions. Very simple example, here is this avatar, which would help you learn how to count on your fingers. However, recent research in virtual reality explored how we could manipulate hands with different fingers, how can we connect with those hands. And we could use this to our benefit to help students learn how to count in base 8 or in groups of size 8 and these kinds of research. We can also use semantic avatars to revisit famous embodied learning math activities with reduced split attention effect and a first-person perspective, such as those two examples. And finally, we can also imagine full body semantic avatars. For example, we could imagine an avatar that has stretchable arms to help people learn about 2D linear algebra. So what did we learn into this whole doctorate? First, we built this framework for embodied learning activities and designing those activities. And I think that in future research in that field, we should consider an interdisciplinary approach because all of those perspectives have something to bring on the table. The second thing we looked into is how to design the interaction. And here we found that it's good to consider position-focused approaches, but that we should also explore the gap between bodily action and interaction. And there's an opportunity here for design that can help learning. Then looking at different learners, we found that we can support math-anxious individuals and highly body-aware individuals with virtual reality embodied learning activities. But we also found that we can design beyond position and movement, for example, integrating muscle tension in interaction design. Looking at the context of the interaction, we found that we can utilize embodied concreteness to ground mathematics by designing according to this. And then we also looked at the avatars and we showed that we can actually utilize those digital avatars to elicit bodily actions and create meaning. So there's this whole design space that's very exciting to explore. Of course, there are some limitations to this work. So one big limitation is the low number of participants in the first derivative study. For my defense, this happened during the whole pandemic, so it was really difficult to conduct any study at all. Then we also have like cross-technological studies where one condition is implemented on tablet, the other one in virtual reality, etc. And this was a conscious decision because I knew I had limited number of participants. And so every time I decided to focus on the technology that can convey the experience that I want to convey. Because for example, having an abstract non-interactive condition in virtual reality would not be fair for that condition because as soon as the students put the VR headset, they expect to see things, they expect to manipulate things. So it would like bias negatively the condition. Then there's also space for future work. So one thing we should do is explore the social context, both in the physical world and in the virtual world. We should also explore a tangible physical context. So what if I have haptic feedback and actually feel the things that I'm manipulating? And then I would be very interested in exploring the role of sensory-motor individual differences. Because if we really learn and interact through our bodies, we all have different ways of perceiving the world, we all have different ways of acting on the world, we all have different bodies, and this has to play a role in how we design those activities. So I think this is very interesting to explore in future work. So now what is the future of VR embodied learning? And one thing I'm quite excited about is what I called in VR embodied assessment. This has different motivations. One is that I noticed in those empirical studies of embodied learning, we really struggle to find significantly positive learning outcomes. So I was wondering, maybe it just doesn't work that well, or maybe we're not assessing learning properly. And then I started looking into how students express their understanding. And there's this theory that first we can express understanding through gestures, before we can express it through speech, and before we can express it through writing. And sometimes we have this inconsistency where the hand is correct, but the speech is incorrect. So for example, students would say, oh, and here the slope is decreasing. The hand is correct, but the speech is not correct. And then I thought when we do those studies, we actually evaluate learning at the writing level, or sometimes at the speech level, but very rarely at the gesture level, or it's very cumbersome to do. And I feel that for those kinds of studies where we really focus on intuition building and embodied understanding, we need to be able to evaluate things at the gesture level. We need to be able to evaluate this evidence of preliminary learning. And that's where, from the VR perspective, we can actually contribute. We can First, we can help identify preliminary learning by observing how people move in VR. And we can also support math-anxious and highly body-aware individuals by giving them assessment methods that actually capture better how well they are performing. So I think for the future, it's very exciting to explore this kind of topic on how do we assess embodied learning altogether and whether we can actually use the technology we have to support this direction. There are a bunch of contributions from this work, which I will also list in the description below if you want to read the different papers to have more information on what I spoke about today. And I would like to thank you very much for going through this video. I hope that you learned something interesting today. I hope that it opened a new perspective for you on how to design embodied learning activities. And if you're interested in discussing more, please reach out. Thank you.